Welcome to my YouTube channel called A Big Structure Hub, and today I want to analyze a question from a past paper, that is Knec Module 1, Structures 1, June, July 2020. So the question reads, Figure 5 shows a loaded beam. This is the beam. Determine the reaction at the support, that's Roman 1. Roman 2, sketch shear force and bending moment diagrams. And then Roman 3, sketch the bending moment diagram. The question is 10 marks. So the first thing to do, as usual, extend this line to give you space to draw a shear force and bending moment diagram. And you should do it on one page, not on separate pages. So extend the line until it gives you enough space to draw your diagrams. So like that. And then the second thing is to calculate the reaction. And as you can see, this is a single span overhanging beam. So we will use the three equations of equilibrium to determine the reaction at A and B. So let's begin by summing moment about a point. So solution, summation of moment at A should give you 0. So after that, we will be calculating the reaction at B. So in which direction is B moving in reference to point A? So it is moving this way. So that is anti-clockwise. So minus RB times the distance from A to B. So it is 2 plus 1 plus 2. So that is 5. And then the force which is so close to A is 10 kilonewton. In which direction? This direction. As you can see, anti-clockwise, negative 10 times 1, because from this load to A we have 1 meter, and then we have 15 kilonewton per meter IUDL. So in which direction? It begins from this point, it ends here. So this direction. So that is clockwise. So plus 15 times 2. When you are working with ADL, you change it first to a point load by multiplying the distance. And then after that, you will multiply by a half of that distance covered, because the UDL, the bending moment for UDL, it acts at the center of that distance of UDL covered. So times times 2 over 2. You close the bracket, and then we have another one, 20 kilonewton. That is a point load. In which direction? Clockwise. So plus 20 times the distance from here to where 20 kilonewton is 2 plus 1, that is 3. Okay, the final one is 8 kilonewton per meter. That is a UDL. So it begins here, it ends here. So it is moving in clockwise direction. So plus 8 times 2, change first to point load, and then times 2 over 2, the bending moment act at the center of that beam, then add the remaining distance from A to here, that is 2 plus 1, that is 3, plus 3, is there any other force? No, should give you 0. After doing so, now you can open the bracket by saying that minus 5 RB minus 10 plus here 1, here 1. So that is 30 plus that is 60 plus here 1, here 1. So that is 1 plus 3, that is 4. 4 times 2, 8. 8 times 8, 64. Should give you 0. Minus 5 RB minus 10 plus 30, that is 20. 20 plus 60, that is 80. 80 plus 64, that is 144. So plus 144 should give you 0. So 5 RB should give you 144. You divide both sides by 5, which implies RB equals to 28.8 kilonewton. So that is our RB, 28.8 kilonewton. So the next thing is to calculate the reaction at A. And how do you calculate the reaction at A? You can sum moment about point B, or use one of the equation of equilibrium. So I want to use one of the equation of equilibrium, which says that summation of upward forces should be equal to summation of downward forces. So summation of upward forces should be equal to summation of downward forces. So the summation of upward forces is reaction A plus reaction B, and summation of downward forces, you have 10 plus 15 times 2, you are changing linearly to a point load, so plus 30, and then plus 20 plus 8 times 2, you are changing linearly to a point load, that is 16, like that. So already we have RB, so you can comfortably replace RB by its value. So that is 28.8 should give you 10 plus 30, that is 40. 40 plus 20, that is 60. 60 plus 16, that is 76. So this implies RA equals to 76 minus 28 0.8. So RA equals to, take your calculator and carry out the operation. 47.2. So RA equals to 47.2. kilonewton. Very correct. So after doing so, the next thing to do is to draw the shear force diagram. Let me use another pen. And how do you draw a shear force diagram? You first draw a baseline. So this is our baseline. And say shear force diagram. We begin at C. At C, we have a loading which is on the top of the beam. So it will be a negative shear force. So you approximate where you think 10 can be. So below the baseline is negative, above the baseline is positive. So let's approximate. So let's say our 10 is around there, and give it a figure which is 10. So it will be constant up to the next force, which is a reaction at A. So that's negative 10. Take negative 10 plus reaction at A. So negative 10 plus reaction at A, which is 47.2. That's 7.2. So you will approximate that 7.2 somewhere, let's say somewhere like there. So that's 7.2. After that 7.2 will subtract this UDL, which is 15 kilonewton per meter, but you first convert it to point load by multiplying distance covered by that UDL. So minus 15 times 2, that is 30. So you get 7.2. So let's say 7.2 is around here. So you draw a diagonal line like that. So that is 7.2. There is not any force here, so it will be constant up to the next force or the next loading, which is 20. So you will take that 7.2 minus 20. So you will get negative 12.8. So negative 12.8 is around there. So we have the line extending up to there, and then give it 12.8. Give it a value 12.8. This negative 12.8 minus again a UDL, which is 8 kilonewton per meter. Convert it first to a point load by multiplying the distance. So that is 8 times that is 16. Negative 12.2 minus 16. That is negative 28.8. So it's around there. Yes. So we have 28.8. So negative 28.8, negative 28.8, add reaction at B. Negative 28.8, add reaction at B, which is 28.8. It will bring you back to 0. So this is 0. The bending moments. Like that. So we know that bending moment at C is equal to bending moment at B and is equal to 0. At C, this portion is overhanging, so this at point C, it cannot create any moment because there is no, it is not a span. And here is a pinned support, so its bending moment is 0. So let's go to bending moment. Bending moment at A. At A, it will be the area of this, this rectangle. So it will be 10, negative 10 times 1. Why negative 10? Because this diagram is below the baseline, and they said shear force diagram below the baseline is negative. So the answer is negative 10 kilonewton meter. Again, the other thing to know about bending moment at C and B, we know from the definition of bending moment. So bending moment is the algebraic sum of moment either on the left side of the beam or on the right side of the beam. So at C, if you can see here at C, there is no any figure that is beyond C to give us a bending moment. And also at B, there is no any figure beyond B to give us a bending moment. So let's move at point D. Bending moment at D. At D, it will be bending moment at A plus the area of this shape, this one, the area of this shape. As you can see, this is a trapezium, so it will be a half into brackets at 7.2 plus 7.2 multiply the h 2. This is the h from here to here. So we have bending moment at A, we have negative 10 plus here 1, here 1. So that's 7.2. That's 7.2 plus 7.2. You get 44.4. So that is 44.4. So which imply and bending moment at D equals to 34.4 kilonewton meter. So that is bending moment at point D. So let's move to point E. So bending moment at E. At E, it will be bending moment at D plus bending moment at D here plus this area. As you can see, this is a rectangle. So the area of a rectangle is length times width plus 7.2 times 1. So this one will be 34.4 plus 7.2. So this one will be 41.6 kilonewton meter. So that is the bending moment at E. Now we have all the values for bending moments. Let's now draw our bending moment diagram comfortably. The first thing to do is to draw a baseline. So draw a baseline. So that is bending moment diagram. At point C is 0. At point C is 0. At point A is -10. At point A is -10. So at point A is -10. So let's approximate somewhere like there. So that is 10. So draw a straight line. Draw a diagonal line, not a straight line. A diagonal line for the point load, and then a curve for UDL. Like that. And then at D we have 34.4. At D we have 34.4. So at D, let's approximate and say this is 34.4. So this one, it will be a curve because it is a UDL, so 34.4. Then we have at point E, this one. At point E, we have 41.6. Let's approximate somewhere like there. So this is 41.6. So again, this one is a straight, is a diagonal line, not a straight line. Like that. And then bending moment at B is 0. So here it goes back to 0, but use a smooth curve because it is a UDL, so it goes back to 0, like that. So this is negative, this is positive. Like that. So guys, I want to add an addition information, and this is all about the point of contraflexion. Point of contraflexion. Point of contraflexion. The point of contraflexion. This is a point where the bending moment changes sign from positive to negative, or vice versa. And the bending moment is always equal to 0. As you can see this point, let's call this point y. So point y from the diagram y equals to point of contraflexion. Like that. So at times you may be told to calculate the distance from the left hand side of the beam or the right hand of the beam to the point of contraflexion. For example, let's call this distance C. You calculate that distance C. How will you go about such a question? I want to take this part, to scoop this part, and draw it here. So we have something like this, and then we have a point load 10 kilonewton, and then here we have a reaction, and then here, this is where we have our point of contraflexion, that is y, and then from here we have a UDL. So like that. So this one is a UDL. So that is 1. This is C. So this one will be C minus 1. And this is A. This point A. Now, for you to calculate distance C, you will take moment about point Y. So moment at Y. So this one will be we have this 10 kilonewton in each direction. That is negative 10 times C from here to where Y is. We have reaction A in each direction this way, that is clockwise, so plus RA times C minus 1. C minus 1 because the distance from here is C minus 1. And then we have a UDL from here to here. It begins here. So again anti-clockwise minus minus 15 times c minus 1 times c minus 1 over 2. Like that. And then we'll open the bracket. We have negative 10c negative 10c, this one, plus RA is the value for RA is 47.2. So 47.2 into bracket c minus 1. Then you count this one, minus 15 open this bracket. We have c square minus c plus 1. So we have negative 10c plus 47.2c minus 47.2 minus 15 over 2. We have c square minus 2c plus 1 should give you 0, because bending moment is 0. Then we'll find the value of c.